Assalamualaikum and a very good day to everyone. Today I would like to talk about stability of a control system. Before we can design controller of a system, we need to check if the system is stable or not stable. In order for us to check stability of a control system, there are few ways of doing that. I will show you in this recorded session how to check stability of a control. Let's talk about the concept of stability in control system. A system with a dynamically bounded input, if an input applied to a system is a bounded input, then the system responds with a bounded response, then the system is said to be stable. So it means to say that if the response does not grow with time, then system is definitely a stable system. Alright, this is an example of several input to a system that we can check the output of the response. Okay, so if I apply impulse input and the response is also a bounded response, then the system is said to be stable. For example, step input is also a bounded input, and any other input which is not growing with time, if you apply to a system, then the system is also doesn't increase, the response doesn't increase with time, then these are said to be stable system. So if you look at the last response here, okay, for if the system is actually growing, the response is getting bigger and bigger, then the system is said to be unbounded. So it means to say the system is unstable. Okay, let's have a look at this first example. Let's say I have a system with a first order system and the transfer function is 1 over s plus 1. So if I apply an input which is a step input to the system, step input is a bounded input, okay, because it doesn't grow with time. If I apply to this system and I need to check the response, so what happened to the system, all right? So I can do that using mathematical equation. So let's have a look at the how does it work, all right? So if we apply u is equals 1 over s multiply with the transfer function, ys will become 1 over s plus 1. Okay, so if we take partial fraction for this system, it becomes ys is equals to 1 over s minus 1 over s plus 1. Okay, see, we can get this using partial fractions, right? So then after that, using this partial fraction, the equation ys, we can further determine the yt, the time response of the system, by taking inverse Laplace of the system. And inverse Laplace of the system, of course, 1 over s will give you 1, and then 1 over s plus 1 will give you an exponential, okay, where the alpha value is actually plus 1, so it becoming exponential of minus t. You need to recall your Laplace transformation for this, okay? And then from that, we can check if I plot the response by giving value of t from t equals to 0 to t equals to infinity. Okay, when I plot the response, it will give me a negative exponential response. Okay, negative exponential system with this kind of response is actually a stable system. Okay, let's have a look how does it works in terms of mathematics. Okay, so we have this system, gs is equals to 1 over s. Okay, so 1 over s plus 1. So we apply input, which is a step input to the system, and we want to check what is the response of the system. All right, so if us is equals to 1 over s, all right, so if I multiply with my transfer function, because you know the response ys is equals to 1 over s plus 1 multiplied by 1 over s, which is your input to the system. All right, so it means then I can actually do partial fractions by just saying that this is equals to a over s plus b over s plus 1. Okay, so when we do partial fractions, it means to say I'm going to cross multiply these. Okay, and the whole lot is divided by s plus 1. Okay, so what happened to this? We can actually then say that, oh, this is actually equivalent to our previous equation, which is here, isn't it? It's 1 over s plus 1, which is equivalent to this. Okay, so this is equivalent to that. So what we do is, with this equation, we then do the comparing the coefficients of the numerator, because the denominator is already similar to the equation on top. Okay, so we need to actually compare to the numerator of the system. So if I compare the coefficients, I'm just going to compare the numerator, because numerator is now what we want to know. We want to find out the transfer function. Okay, so then if I compare s to the power of 0, on one side it will have 1, on the other, sorry, not 1, it's a. On the other side it's going to give me 1. Therefore, I straight away know that a is equals to 1. Okay, and then if I compare the coefficients on the other side of s to the power of 1, I will have 1 is actually a, the other one is plus b, and then the coefficient on the other side is 0. So from there I can tell that a is equals to minus b, therefore b is equals to minus 1. Okay, so from there we can put this back into our equations. Then we're going to have our ys is equals to 1 over s minus 1 over s plus 1. Alright, so by having this, we can actually do the partial fraction. We've done the partial fractions. Okay, so we need to actually find the Laplace transform. So if you remember Laplace transformation, right, I'm taking Laplace transformation of ys, it will give me yt. Okay, inverse Laplace of 1 over s will give me 1. Okay, and inverse Laplace of 1 over s plus 1 will give me 1 multiplied by exponential of minus 1 multiplied by t. Okay, so if I have that exponential of minus t there, what happens is that if I plot the graph by giving value of, for example, we start with t is equals to 0. So if I have substitute t equals to 0 into my negative negative exponential, it will give me value of 1. Okay, 1 minus 1 is, of course, that's going to give me 0. So you will start with y is equals to 0. And when this is when t equals to 0. When t equals to infinity, okay, yt will become equals, it's going to be equals to 1 in this case. All right, so if I plot the graph, okay, my input that I like is a step input, right, with value of 1. Okay, and then what happened is that my response will become negative exponential, and the value is also, the response will also become 1 eventually, okay, when t equals to infinity. All right, so this is how my system responded. So this system is said to be a stable system, which is good, right? So let's have a look what happened if our value of transfer function, instead of s plus 1, what happened if it's s minus 1? Okay, so similarly, you will do the similar process, okay, but what happened now, the value is becoming, the transfer function is 1 minus 1 over s plus 1. Okay, so I have ys, this is second example, okay. Ys is now equals to 1 over s minus 1 multiplied by my us, and for that, for the method of comparison, we will use the same input as is, us is 1 over s. So I'm going to have then ys is equals to 1 over s minus 1 multiplied by my input 1 over s, and then what happened is that again I'm going to have this as a multiplication of that will give me 1 over s minus 1. Okay, again I'm going to do these as a partial fractions with a over s and minus b, plus b s minus 1. Okay, when I do partial fractions for these, okay, what I'm going to have is that, okay, this is how we're going to do, we cross multiply that. I'm going to have as minus a plus bs over ss minus 1. Okay, right, so the denominator is already the same, so we just need to compare coefficients of our numerator. Okay, so comparing coefficient of s 0, on one side I will have, so it's going to be minus a. On the other side, I will have it's equals to 1. Therefore, I straight away know that my a is equals to minus 1. Okay, that's for comparing the first coefficient. Let's compare then s to the power of 1. What happens is with this s to the power of 1? On one side, I will have a plus b. On the other side, I will have it as 0. Okay, so from there, I know a is equals to minus b. Therefore, b is equals to 1, because since a is minus 1, then of course b will be 1. So then we put that back into our equation. Ys is equals to minus 1 over s plus 1 over s minus 1. Okay, so it doesn't really matter what is your numerator. You can see that the denominator will actually affect your stability. Why? Okay, let's take Laplace transform of this. If I take inverse Laplace, not Laplace transform, sorry, it's inverse Laplace of ys, that will give me yt. Okay, and then if I take inverse Laplace of my 1 over s, it gives me 1. But of course, there's a minus value there because the coefficient is minus 1. Okay, and this part will give me exponential of, instead of having minus t, because now your part here is a minus 1, so it's going to give you positive t. Okay, so this positive t, if we plot, it will give you a positive exponential. So how does that looks like? All right, so of course, just now this is our response. We want it to be a step input of value of 1. Just now we are giving to the system. So when I apply, when t is equals to 0, okay, oops, when t is equals to 0, yt is equals to 0. But when t is equals to infinity, if you put into this equation, because of that positive exponential, your yt will become infinity, and that's how it will respond. Okay, so this is then showing you that the system is unstable. All right, so this is the concept of stability. So if you look at the equation, the difference just now, which part will determine the instability of the system? By looking at the transfer function, the denominator of your transfer function will determine if your system is having a stable or unstable system. All right, so let's have a look at another example. Okay, example number 3. So what happened is that let's say you are given another transfer function, which is s plus 1 over s plus 3 plus s plus 2. Okay, so you need to determine the stability of the system. All right, by looking at the previous one, actually we can do the similar process, doing the partial fractions, comparing the partial fractions, the coefficient of your partial fractions, and obtain the yt by doing inverse Laplace. You can do that. Okay, but by looking at this, okay, we can just simply do the same procedure. Multiply that with, let's say it's a step input, again step input, or you can just give you, instead of step input, we can also give you impulse input. For example, us is equals to 1 is an impulse input, okay, to the system. All right, it doesn't matter if you want to give step input or impulse input. So in this case, I'm giving an impulse input while us is equals to 1. Impulse input is also a bounded input. Okay, right. So what happened is that we are doing partial fractions again. All right, but if I don't want to do partial fractions, I'm just going to say that, let's say it is equals to a over s plus 2 plus b over s plus 3. No matter whatever the value of your a and b, okay, the stability of the system is actually affected by your denominator, not the value of your a and b. Okay, how is that so? If I take inverse Laplace of ys, that will give me yt, isn't it? If I take inverse Laplace of my a over s plus 2, that will give me my a exponential of minus 2t. All right, that minus exponential will give you a stable system, plus b exponential of minus 3t. Okay, so that negative exponential will actually give you a stable system. If I put the system y, okay, from time t equals to 0 until t equals to infinity, your y will actually approach 0, and then your response is said to be a bounded response. So in this case, it's a bounded response with a bounded input. Okay, so this is mean the system is stable. All right, so how does the what happen when the system is unstable? All right, so actually if you look at this equation, I'm just going to quickly show the stability is determined by that part here, the negative exponential of the system. What if that negative of exponential, instead of is a negative exponential, what if it is a positive exponential? What if the system is yt equals to a exponential of positive 2t plus b exponential of positive 3t? Then definitely, even with one value here, if I plot, then it's gonna give me a big value, isn't it? It's gonna give me a positive exponential value. It means to say the system will become unstable. How can I get a positive value as my exponential? They actually depend on my denominator of my transfer function. So in this case, that denominator, if it having a s minus 2 or s minus 3, then the system will become unstable. So it's as simple as that. So it can come from my transfer function ys. If ys is equals to, let's say, s plus 1 over one of them, s minus 2, as let's say the other one is positive, s plus 3. Okay, so if you take Laplace transform of these, you're gonna get a of exponential of that minus 2 will give you positive 2t, and that s plus 3 will give you a negative 3t. So only with one value of minus 2 at the bottom of your transfer function will give you a positive exponential, and hence with that positive exponential, your system will be unstable. Okay, so that's how you look at these two. There's another way of checking if the system is stable or not, okay, by defining your poles. All right, so it's a stability of a system, of a feedback system, is also can be defined by the value of your poles. All right, so let's have a look at value of poles. What does it mean by the value of poles? All right, to obtain a bounded response, poles of a closed loop system must lie in the left hand side of the S-plane diagram. You know, for S, for Laplace, we can actually plot Laplace because Laplace is a complex number. So we can plot the graph of Laplace, okay, with the value of imaginary against real in the what we call S-plane diagram. Okay, I will show you later on. Right? The system is said to be unstable if any of the roots are in the right hand side of the diagram. So how is that? Let's have a look at concept of zero and poles. Okay, so let's consider a system with a closed loop function like that. Okay, so you have your y over u is equals to g over 1 plus gh. Okay, and the denominator, I've shown you from the previous example, you've seen that the numerator does not affect the stability of the system, but the denominator of the system does. Okay, so from this closed loop transfer function, 1 plus gh equals to 0, which is the denominator of the system, is also known as a characteristic system of a characteristic equation of the system. Characteristic equation means that it actually can tell you what is the character of the system. All right, so in this case, with this value, all right, so we can actually either write your transfer function in form of polynomial form. Okay, so if you have a transfer function, it can be in a polynomial form, but you can also write your transfer function in what we call zero poles form. So by actually factorizing your polynomial, you can actually convert the polynomial into zero poles form. Okay, so when you have your zero and poles form, when you do your inverse Laplace, you can check if the system is stable or not by looking at the value of your poles, isn't it? From the if you remember this from the previous one. So let's say we have like this, ys is equals to this, I've already put in Laplace, in the polynomial in a zero and poles form, where the denominator will give me my zeros and the denominator will give me my poles, my numerator will give me my zeros. If I take Laplace transform, before that, if I can do partial fractions, I will get my value of partial fraction as such. And then if I take the inverse Laplace, this is what I'll get. I'll show you in mathematics form. Okay, let's have a look if I have this in terms of some example. Okay, let's have a look in an example. So let's say I have a system ys is equals maybe ys over us, trans function is equals to, let's say I have say s plus 4 maybe, okay, over I have s squared plus 3s plus 2. Alright, this is in a polynomial form. So from polynomial form, let's say I want to convert to zero and poles form. If it's zero and poles, I need to factorize this polynomial, right? So in zero and poles form, it simply means I'm factorizing it. Okay, in this case, the numerator cannot be factorized anymore. So it's going to be s plus 4. The denominator can be factorized by having s plus 1, s plus 2. Okay, so this is already in zero and poles form. Okay, so what does it mean? If you look at the numerator of the system, that will give you the value of your zeros. The denominator here will give you the value of your poles, alright? So in this case, if I define my zeros, it is actually s equals to minus 4. So that is the value of your zeros. And the value of your poles is, in this case, is s is equals to 1 minus, s is equals to minus 1. And then s is equals to minus 2. This is your poles, alright? So this is means by having the transfer function in zero and poles form. Right, so having the value in terms of zero and poles, similarly, as before, I can do partial fraction by multiplying this system with an impulse input, for example. So I can just do ys is equals to s plus 4 over s plus 1, s plus 2, multiplied by 1. Okay, why 1? Because us is, let's say, is equals to 1. This is coming from impulse input. Okay, so having to have that, I can just do cross multiply and then I can do partial fractions. All right, so I'm not going to do that. I'm just going to call that a over s plus 1 plus b over s plus 2. Okay, why I'm doing this? I'm going to just show you similarly like before. Okay, by doing inverse Laplace, you're going to get this equals to yt. All right. And you're going to get that a is still a, but the exponential 1 over s plus 1 become exponential of minus 1t, okay, plus b exponential of minus 2t. So you see the value of your poles will determine if your system is stable or not, because it's coming from the denominator. So the denominator is actually the value of your poles, right? So you see just now, I've shown you that your poles is minus 1 and minus 2. So if your poles is a negative real value, it will give you a negative exponential value when you do your inverse Laplace. And when you want to plot the graph later on, you'll see that negative exponential will give you a bounded response. So the system is said to be stable. All right. So again, it means to say that there are two ways. One is by doing partial fractions and check from your polynomial, check if the system is stable or not by looking at the denominator. Another way is by looking at the poles of your transfer function. So if you can factorize your system, you can just check the poles of your transfer function. If it's giving you a negative real value, then it means the system is said to be stable. All right. Okay, let's have a look at what happened if this is what I meant just now. Okay, so does the zero affect the stability of the system? Definitely not. The zero of your transfer function does not affect the stability of your system. However, it will affect the transient response of your system. Maybe your system is slower, maybe your system is having steady state error, so maybe your system is having a overshoot. So this is affected by your value of 0, but 0 does not affect the stability of your system. Only poles will affect the stability of your system. All right. Okay, so if you look at 0 and poles, all right, so what happened to this is actually S is coming from the value of S. As I told you, S is actually a complex number. Okay, S is actually we can write S in terms of J omega. S is equals to J omega. So it is actually can be written in a complex number with J is actually equals to negative, or J is equals to square root of minus 1. Okay, so square root of minus 1 is actually coming from J is equals to square root of minus 1. So this is actually showing you just S is actually can be written in terms of complex number. For example, if I write S is equals to A plus BJ, it's a complex number, right? With the real value of A and the imaginary value of B, okay, I can actually plot the graph for my S in what we call S-plane diagram, where I can plot imaginary against real, all right? So for the A is a positive value, let's say it's here, okay, positive value of A, and the B is actually the imaginary value of your graph, okay, so it's there. So your equation S is actually there, all right? So this value is actually referring to, this value here is referring to the transfer function here, okay? So there are several things that we can get from this value, but in this case, this is what we call S-plane, when I plot in terms of imaginary against real diagram. All right, so what happened when our system is unstable just now? Instead of unstable, what happened when the system is a stable system just now? You've seen that for a stable system, okay, the roots of your system must be in a positive, in the negative real value, okay? So if it's in the negative real, then the system was stable. You remember just now your S is equals to minus 2, S is equals to minus 3 or minus 1, I think. Okay, so if this is minus 1, this is minus 2, then the system is said to be stable. If your value of S lies on this side, this is the unstable side. Okay, why is it so? Because if I have one value here, is let's say my poles is equals to S equals to minus 4, for example, all right, how does it happen? How can I get S is equals to minus 4? Maybe my equation or my transfer function is equals to this, isn't it? Not minus 4, sorry, positive 4. Okay, so it can come from the value of something like that, okay, transfer function of 1 over S minus 4, all right? So then if I look at the poles here, okay, it's going to give me S equals to 4, all right? So that will give me, if I take Laplace transform and I do, inverse Laplace to this, I will get my GS in terms of YS maybe, right? One over S minus 4, okay? So what happened is that if I apply impulse input with value of US equals to 1, this is going to give me S minus 4, and you have seen this, right, multiplied by 1, all right? So you have seen that if I take inverse Laplace of YS, that's going to give me YT. Inverse Laplace of 1 over S minus 4 will give me exponential of positive 4t. Positive 4t will give you a very unstable system, okay, because it will give positive exponential value for that, all right? So that means to say the system is unstable, and if you go back, it actually depends on the value of your denominator, which is in this case also means the value of your poles, all right? So If poles is having a positive real value, then the system is said to be unstable. If the poles is having a negative real value, then your system will be unstable. Your system will be stable. So let's have a look at another example. All right, so in this case, very straightforward. Determine the stability of a system with characteristic equation. So straight away, we go to the denominator of your transfer function and we look at the denominator. Let's say it is equals to s cubed plus 4s squared plus 6s plus 4. Okay, let's focus on that. Okay, so the characteristic equation, if I try to factorize it, because I want to put it in zero and poles form, if I factorize it, I will get, okay, from the value of s cubed, it becomes s plus 2 multiplied by s squared plus 2s plus 2, and I equate it with 0 because I want to check where is my poles. Is it on the positive side or on the negative side, right? So then I'll find the roots of my characteristic equation is equals to P1 is equals to minus 2, and P2 and P3 is actually coming from the complex value of s squared plus 2s plus 2. It will give me negative 1 plus j and negative 1 minus j. Okay, so negative 1 plus j and negative 1 minus j, if I plot on my s plane, it is still on the negative hand side. Okay, negative real value. On the negative real value means to say the system is stable. All right, so you can check that as well by taking the doing the partial fractions, doing the inverse Laplace, and then you will get a negative exponential for your system. That means the system is stable. All right, so another example maybe what happens if I have a system looking like this. Okay, it is a closed loop system with a value of 1 over s plus 2 s plus 1. Okay, 1 over s plus 1 s plus 2 is actually a stable system if it's an open loop, isn't it? You already know, okay, because it is, if it's in open loop, if it's an open loop, okay, not a closed loop. Oops, let me show if what happened if it's an open loop. If it's an open loop, okay, for this particular example, all right, it looks like this initially without the closed loop system. Okay, so if it's an open loop, is it stable or not? The question is that. If it's an open loop, is it stable or unstable system? So you can straight away tell that from the looking at the transfer function of the system, all right, so you can tell, okay, by what we have done earlier, either you can tell in terms of the value of poles or in terms of the value of your denominator of closed loop system or transfer function of the system. Okay, so it's going to give me 1 over s plus 1 s plus 2. So if I multiply that with us, and let's say us is a impulse input with the value of 1, so put it there. Okay, impulse input with the value of 1, so definitely this is gonna give me ys is equals to a over, sorry, I missed 1 there, a over s plus b over s plus 1 plus c over s plus 2. Okay, since the denominator doesn't have any negative value there, okay, when you do partial fractions, when you do your inverse Laplace, you're gonna get negative exponential. So negative exponential will always give you a positive, will always give you a stable response. Okay, if I take inverse Laplace of that, that's gonna give me a, that's gonna give me b exponential of minus t, that's going to give me c with exponential of minus 2t. So this system, initially it is a stable system. Alright, so it's already stable. Why do we need to close the loop? Maybe the system is having steady state error. Okay, so maybe the system is having steady state error. We need to control the system, so we close the loop and we add a k controller into it. Okay, so let's have a look at the controller. What happened when the system become closed loop with a controller? So when the system initially it was stable, but then we close the loop and we put a controller into it, and let's say that controller is a simple proportional controller with a value of k equals to 24. Okay, what happened to the system? Right, the stability will definitely change Why? Because when you close the loop and you add controller, your denominator of transfer function will change. So let's have a look at the characteristic equation, which is also similar to the denominator of your closed loop transfer function. Okay, so it's 1 plus GHS equals to 0. So if I put the value of GHS, in this case it was K just now, isn't it? K is 24. This is your G. The G is actually 1 over S plus 1, S plus 2. H is actually the feedback to your system. In this case, H is having a transfer function of 1. Okay, so G, you have to have K multiplied by your G. Alright, and then H is actually multiplied by 1. So that's what we have, 1 plus G, which is your 1 over S plus 2 multiplied by 24. Okay, then multiply by H, which is 1. Equate that with 0. If I cross multiply the denominator and equate the denominator, then I will have this polynomial S cubed plus 3S squared plus 2S plus 24 equals to 0. Okay, then from there, if I find the roots of my system, that will give me P1, the first poles. Okay, poles 1 is equals to minus 4. I can straight away say poles because this is coming from characteristic equation. You have seen earlier, the characteristic equation will give me the poles of my system, not the 0. The 0 coming from the numerator. Okay, characteristic equation is the denominator of your closed loop transfer function. So poles number 1, that's why I put P1 there, is equals to minus 4. P2 and 3 is a polynomial. Okay, it's coming from my complex poles. Okay, so complex poles is then giving me 1 over 2 plus minus J 2.4. Okay, so we have two complex and conjugate poles, which is positive half plus 2.4J and positive half minus 2.4J. So if I plot that graph, you will see that the complex and the conjugate poles will be having the value of positive real value. So since it's a positive real, it will lies on the unstable region of your closed loop or on your S-plane diagram. So your S-plane diagram will have a positive real value poles. So the system is definitely unstable. How do we know this? We can check it further by plotting we can plot the graph by doing the partial fractions and inverse Laplace and then plot your graph. You will see that the system is unstable. Okay, you can do that, or we can just believe or trust on the poles value based on our what we have proved earlier, that stability can also be defined by the location of your pole. So in this case, the location of poles is on the positive real, so the system is unstable. If the poles is on the negative real, the system will be a stable system. All right, so that will be all for now. Okay, for stability. All right, so I will see you in the next video when I will talk about steady state error of a system, of a closed loop system.